Functional connectivity. Functional connectivity is a measure of statistical dependence between signals. Effective connectivity implicates causal dependence between signals. It shows direction of the transmission. Connectivity measures involve linear, nonlinear, bivariate, and multivariate methods. When choosing the method, one should consider characteristics of a time series. e.g., is a very noisy signal. Nonlinear measures of connectivity are very sensitive to noise and arbitrary choices of parameters. Besides, it was demonstrated by signals forecasting and surrogate data tests that DG does not show distinct traces of nonlinearity. Some people assume that neuron acts in nonlinear way, so EEG, which comes from the neural action, also is nonlinear. And that is a primitive thinking, because EEG is superposition of the action of many neural populations. So in practice, it is similar to the colored noise, that in other words, a noise with some specific frequencies, some specific oscillations. Now, the bivariate methods provide only functional, not causal connectivity, are unable to determine reciprocal connections, and are prone to common drive effect, which leads to the generation of false connections. I'll talk about this common drive effect shortly. We shall concentrate here on linear multivariate methods, since they are robust in respect of noise, are free of common drive effect, detect reciprocal connections, and provide causal coupling between signals. The testable definition of causality between time series was introduced by Granger in the field of economics. Granger defined causality in terms of predictability of time series. So if some series X2 contains information that in past term that helps in the prediction of series X1, then X2 is said to cause X1. Granger causality principle may be expressed by two-channel autoregressive model, so which means that X1 can be predicted not only by the preceding samples of signal X1, but also by the samples of signal X2. This is A12 coefficient. Now, multivariate autoregressive model. Granger causality was introduced for two channels. However, as was pointed out later by Granger himself, test of causality is impossible unless the set of interacting channels is complete. It is especially important in case of EG. Granger causality was extended to arbitrary number of channels in the framework of multivariate autoregressive model. So where X is a vector of K signals, so we have a set of signals, AJ is K as a K matrix of model coefficients, E of T is a K-size vector of white noises. P is the model order. So what it says is that, let's say the sample X, is this mouse, that the sample xt of the signal X can be expressed as the preceding samples of X signal and are multiplied by some coefficients, and also by the samples of other signals of the set, also multiplied by some coefficients, plus white noise. Marr model can be transferred to the frequency domain, and then it has a form. And H is a transfer matrix of a model, which is expressed by the inverse of the model coefficient, matrix of model coefficients. it can be illustrated as a black box model with the white noises at the input, a time series at the output, and the information about the relations between the signals is contained in this transfer function. So the directed transfer function, introduced by us in 1991, was formulated for arbitrary number of channels and was based on the transfer function, transfer matrix of the MEVAR model. It is normalized in such a way that transmission from channel J to I at function F is normalized in respect of inflows to the destination channel I. However, also non-normalized directed transfer function sometimes is used when we want to know compare the strengths of the connections. So delta F is robust in respect to noise. It shows causal coupling between time series, contrary to bivariate measures, such as correlation or coherence, which yield only function statistical dependence. This function is able to find reciprocal connections and is free from common drive effect. So now I would like to show that it is really robust in respect to random noise. So this is a very simple simulation. The activity from channel 1, it is just UG signal, is propagating to channels 2 and 3 with some delay, and noise also is added, and it's a random noise of the amplitude 3 times as big as the signal itself. So the variance, noise to variance, is 9 times as big. So we cannot perceive the signal in the noise. Nevertheless, the direction of propagation can be still determined. Now, how to read this kind of a picture? Because I'll show some more of this with a bigger number of channels. So on the diagonal, we have power spectra. And then in each box, non-diagonal box, the directed transfer function as a function of frequency is shown. And the propagation is from the channel which is marked above to the channel marked at the left. So here we have propagation from channel 1 to 2 and from channel 1 to 3. And let's say from channel 2 to 1 or 2 to 3, we have only some residual values not connected with the noise. Now, I would like to explain this common drive effect. So let's say we have the bivariate estimator. It doesn't matter which one. The correlation, coherence, and can be also two-channel DTL. And now we already know that this scheme shows the propagation from channel 1 to 2, 3, 4, 5, but we can see that in not only these simulated directions are shown, but in case of bivariate measure, also bivariate measure shows also connections between the destination, all the destinations channels, because they are fed from the same source, so they show similar activity. So if activity is spreading from the source and is registered at n electrodes, then n true and n minus 1 by 2 false connections are produced. So number of false connections can be bigger than the true ones. For the multivariate estimator, we have the same result as the simulation shows. Now let's come to the real data. So this is DTF functions for the EEG registered during sleep by 21 electrodes. And in this case, the channel from the activity spreading is marked at the bottom of this picture. And we can see that we have, if some channel is propagating activity, usually it is It's propagating to almost all the other destinations, but at a different rate. Here you can also see but maybe it's a very small corridors of errors. And now we can illustrate this experiment, the results, by means of arrows. And then for wakefulness, the propagation is from the back of the head. It is known from Hans-Berger time that the main sources of the activity during eyes closed wakefulness are at the back of the head. Here we have, let's say, many arrows because it's averaged over 9 subjects, and some people have the sources more at the left, some are more at the right hemisphere, some in the middle, so it looks like this. And then in stage 1, which is a light sleep, this picture becomes more organized. At stage 2, at this stage, so-called sleep spindles are generated, and there are 2 kinds of the spindles, and it shows 2 sources of activity. Now, stage 3 plus 4, it's a deep sleep. So then whole brain is working at one pace in low frequency, and it's very much coherent and correlated. The propagation is mainly from FZ, and FZ is an electrode which is located exactly above the so-called corpus callosum. And corpus callosum is a structure wherefrom all the main neural tracts are propagating forward and backward. So it is quite understandable that in case of such a deep sleep, all the activity is somehow generated, probably from the structures under cortical structures, and then propagated through FZ electrode. Now, for comparison, we have the picture of connections also in stage 3 plus 4. Also in the same work, where the connectivity was estimated by the varied measure, synchronization likelihood, but it's not important, no significant changes in network parameters were found for different sleep stages, which is contrary to what we have observed several years earlier. Now, I'll say a few words about experiment of finger movement and its imagination. This kind of experiment is performed quite often because imagination of right or left finger movement is one of the paradigms of brain-computer interface. So let's say left finger 0, right finger 1, or inverse. A little bit of anatomy. So different parts of the brain are devoted to different functions. And this red one is a motor cortex. And this motor cortex, it goes around the crown of the head. And certain parts of it are devoted to different body parts. And a large part of it is devoted to the face because it's mimics. And also quite a large part for the hand, because these are precise movements. Another thing that we know about this is if we look at the particular rhythms, here is the movement, is this vertical line. So before movement, the alpha rhythm and beta rhythms are decreasing. It is so-called desynchronization. Then we have beta rebound, and we have a rise of activity in the gamma band. So if we would like to see dynamically and how it works, then we can calculate so-called short time directed transfer function. In this way, that we take a small window, but then we take into account, we can perform ensemble averaging across the repetitions of the experiment. So the correlation matrices used for coefficients calculation are averaged over realization. So now we can see dynamically this finger movement experiment. Now, in this case, directions are usual, okay, from the channel mark here to channel mark to the left. And horizontal axis now is the time axis, and 0 is the time of the movement. And let's look at the, let's say, C5 electrode. We can see a gap in the propagation in the alpha and beta band, and a little bit of rebound. But if we looked at electrodes C3, and electrode C3 is exactly above the motor cortex of the index finger. So in this case, this desynchronization, the decrease of alpha and beta, is more pronounced. And then in some frontal electrodes, towards C3, we can see also the in a very pronounced way, this beta rebound. And this was for this alpha and beta. If you would like to look at the gamma, we have to filter out these lower frequencies because gamma is very much damped by the head structures. And besides, it is due to smaller populations of neurons. So it is much more demanding. Nevertheless, we have calculated the propagation in the gamma band, which I will show by means of this animation. So please watch when the red Q will appear on the screen. So this is before, okay? And now we wait for the Q. And after Q, we'll see the burst of activity from C3 in case of movement, and then nothing much more. And then please look at the imagination. In this case, it is all later, and we have not only propagation from C3, but some kind of crosstalk between this C3 and the electrodes, which are placed above the sensory motor cortex, not only primary motor cortex in the index finger cortex, but also above the other sensory motor structures, because it is more demanding task. Okay. Now another experiment. It is information transfer during a working memory task. And in this case, it was such a task consisted of memorizing letters and relations between them. And here are the results of fMRI experiments. So in fMRI, so we have just certain places, certain structures, certain pixels which are activated. And in this case, we have that it's in the front of the head and in the back of the head. And now we look at the propagation. And we'll see also that the activity is spreading mostly from this frontal region and posterior region. But we see some more. We see that these two structures are from time to time, only from time to time, are communicating by long-range connections. So sometimes it's from the front to the back, or sometimes it's from the back to the front. So we can observe two centers acting locally, exchanging information from time to time. So in this way, SZF confirmed hypothesis following from scaling rules and track tracing experiment of tightly coupled local areas and less dense long-range connections. And now, this working memory task can be performed using visual or auditory stimuli. And here are the snapshots also from from the movie similar to the one I have shown before, for the visual or for the auditory task. And we can see that they are quite similar. So the patterns of connections for visual and auditory working memory tasks show important role of frontoparietal network in the execution, similar for both modalities. And again, these results support the general hypothesis concerning coupling of structures in a given memory task. Okay, and so in fact, the DF is very much used in the cognitive experiments, like recognition, like recognition of the faces, recognition of emotions, and so on. So of course there are too much to show, but now I'll switch to the examples concerning a clinical application, especially neurodegenerative diseases. I'll show the one about Alzheimer's disease, but it's also used for Parkinson or other diseases or mild cognitive deficits. And EEG is also quite important in case of epilepsy. So in the seminar, the broad study of effectiveness of connectivity measures for Alzheimer's disease diagnostic, where several dozen of methods, linear and nonlinear, were considered, DTF yielded the best result. Okay, it was not all well. However, in the framework of European Union grant, decided the distinction between control group and Alzheimer's disease group based on DTF and spectral changes. We have found quite a good classification between normal and Alzheimer affected group. Sensitivity 0.9 and accuracy almost 0.8. As far as the connectivity is concerned, in fact, the pattern of connectivity did not change very much. This is for the resting state. We know that during resting state, okay, we have propagation from the back of the head, but the strength of the connections changed, and also the rate at which this connection decayed with the distance. Now, a lot of bivariate methods were used also for assessing connectivity in Alzheimer's disease. I'll just show one. And here it's connectivity for norm. Here it is for Alzheimer's disease, and this is the difference. So why it is so difficult to explain? And in fact, the works based on bivariate measures show disorganized this kind of patterns, and in fact quite a contradictory results. Now, epilepsy diagnosis. In case of drug-resistant epilepsy, the removal of the unsaid zone of the ictal activity is performed. It is crucial to exactly identify the focus in order not to disturb important brain functions. Prior to the surgery, the electrodes are implanted in the region preliminarily designed by surface EEG measurements. One of the first DTF applications was identification of the epileptic focus, and this work was performed in Johns Hopkins Medical University, which is leading center for epileptic study. However, the TEP function was introduced by, let's say, our people, Piotr Planaszczuk, who is our former student and collaborator, and Maciej Kamiński present here. So these electrodes, these T electrodes were placed on the cortex, open skull, and H electrodes were depth electrodes in the brain. And we can see that the propagation is mainly from this H5 electrode. So, and then it was confirmed that really this was the primary focus of epilepsy. However, not always the situation was so clear. In another experiment later, which was performed later, prefrontal area was indicated by scalp EEG recording as a potential seizure onset zone. However, the dynamics of ictal activity propagation revealed two epileptic subnetworks, a primary zone. Here we have this primary zone at the time 0, 10 seconds. And then still we have some zone at the back of the head. And then the strongest focus is in front. And this is the one which was identified by the recording from the head itself. And now I'll show the movie illustrating this. Okay, so we have propagation from this primary focus. And it becomes much more, this ictal activity, much stronger than this primary one. So it shows that such an accurate identification of propagation is important for the diagnosis. Now, I would like to point out that the test can be used to find causal coupling between signals of different origin. And two examples, spike train and EEG, and different electrophysiological signals, that is EEG, heart rate variability, hemodynamic, and blood pressure signals. So first, let's look at the direct neurotransmission, because here are the data. So we have in hippocampus, we have hippocampal EEG, and from structure supramammillary nucleus, the spike train was registered. And if we want to look at the interaction of these two phenomena, so we have to do something with some spikes. So they were filtered, low pass filtered, and then some noise was added. And then the DTF was calculated. Here is DTF as a function of time. This is for the hippocampus, from hippocampus to supramammillary. Here is from supramammillary to hippocampus. And we can see that the propagation is mainly from hippocampus, but during the stimulus marked here, also some propagation from this some structure to hippocampus occurs. So the DTF can be also used for point processes. Now that's a little bit more complicated. It's causal coupling between signals of completely different origin. In this case, we have, it was also measurement performed during rest and finger movements. So we measured EEG, but in this case, we have taken into account envelopes of rhythms, because other signals which we measured were much slower, of much lower frequencies than EEG itself. So we took into account the envelopes of alpha and beta rhythms. Then, by means of FNIRS technique, that is functional near-infrared spectroscopy, we have determined the concentration of oxygenated and reduced hemoglobin from the distribution of transmitted photons. I understand that it's not clear, but I don't want to diverge too much from the main line of my talk. So if somebody is interested, I can explain how it is done. So on the scalp, they were placed EEG electrodes, these orange ones, and the blue ones were the optodes, NIRS detectors, and the two red ones were the NIRS sources. We measured also ECG, electrocardiogram, and from ECG, heart rate variability can be easily assessed. And then we have measured blood pressure, systolic and diastolic, from the finger cut. So all 7 signals sampled at the same rate were analyzed by means of DTF, and causal coupling between them was evaluated in this band of Meyer waves range. Mayer waves are interesting phenomenon. They appear in many body signals. However, their generation mechanisms are still enigmatic. Wow. Okay. So this scheme is for the rest, in the rest stage. I don't show this movement because in fact they are quite complicated. So we can see that there are many reciprocal connections, and especially the propagation from blood pressure signals is rather strong. Sorry? Electroencephalogram. Okay, electrocardiogram was measured as well. And from electrocardiogram, heart rate variability was calculated. Okay, what I don't have. So during, so this is for the rest, and during movement, some of these connections become weaker and some disappeared, especially the ones connected with EG alpha and EG beta. We have to remember that we have desynchronization of these rhythms during movement. However, what is interesting is that strong coupling in this loop, heart rate variability and blood pressure, in all this, in the rest as well as during movement, this strong coupling persisted. And also during imagination of movement, which supported the hypothesis of baroreflex origin of Mayer generation. This baroreflex involves interaction exactly between blood pressure, which is measured by baroreceptors, and heart rate. Then also we can see strong interaction of reduced hemoglobin on the oxygenated hemoglobin, which reflects increased demand of oxygen, which is forced by excess of reduced hemoglobin. Now the results suggested a role of Mayer waves in synchronizing different body signals. Why I don't have a time to dwell on it, because in fact all this problem is would require a separate seminar. So no, sorry, don't know what happened. Now let's come to the conclusions. So GTF estimator based on Granger causality principle allows to determine directed interactions, makes possible to estimate dynamical propagation of signals, identifies reciprocal connections, which enables determination of feedback loops, and that is especially, I would say, interesting. It allows to explain information transfer during motor and cognitive tasks, supports diagnosis in neurodegenerative diseases, and helps to determine ictal foci in epilepsy. It can be also used to find causal relations between signals of different origin. And now DTF is a part of all major toolboxes for biological signal analysis, and these original works have more than 1,000 citations. Oh, sorry. Thank you for your attention. Maybe there are some
questions. Thank you very much for this interesting talk. Are there any questions? Yes.
Yes.
Anko, can you take the mic and
What do you mean by noise? What is noise?
Noise is the process which is not connected with the action that we are looking at. So if we want to see the signals correlated with special action, that is not noise, and noise is everything else. And could be, of course, white noise or not white noise.
The background.
The background.
Other questions? Yes. Some.
Personally, I'm curious about whether information is localized on the brain or not.
Sorry,
And based on, and according to your presentation, you identify the information with the electrical signal.
I didn't get to what signal?
Electrical.
Electrical signal.
Yes,
So is it true actually information is localized on the list of brain, or you cannot tell?
okay, the brain, so maybe I'll show. There are certain areas of the brain which are devoted to specific, well, let's say, actions. I have shown you maybe I'll go back to the, sorry. That's great. Oh, where it is? Here. Okay. So here we have a topography of brain, and okay. So here, this red one is it is a motor cortex, and next to it is sensory cortex. And sensory cortex is also organized in similar way as the motor cortex. There are parts of it which are devoted to control of different movements. And then we have occipital and parietal lobe, and for example, it's mainly connected with perception of visual stimuli. And then we have temporal lobe, and for example, this is, let's say, auditory, mainly devoted to auditory stimuli, processing of auditory stimuli and speech. And then we have frontal lobe is connected, it is more like associative. So it is more like integrating different information, let's say calculations, higher actions. And here the small one is olfactory bulb, that is, for olfaction. And let's say in the dog, this part is very big, and in man it's very small, as we can see. So, however, all of these parts of brain, somehow they interact, and the nerves, the networks are very dense. So we might really say that everything is almost connected with everything that may interact, but in a given action, only certain paths of this network is active. So we have communication between certain parts of the brain, and what we try to do is to understand how they interact. So like in this working memory experiment, okay, we have this propagation between frontal lobe, and frontal lobe is more devoted to evaluation of the stimuli, to the integration, and between parietal lobe, and that was the one which also visual, or here in case of auditory, and which takes the stimuli. And here the processing is in front, and these two communicate.
Other questions? Yes, Jan.
Very general question concerning the mechanism of the coupling between the brain and the skin of the skull. Because in principle, one can feel it.
Please, can you say a bit more loudly?
Speak up.
Speak up.
My question concerns the coupling between brain and the surface.
And the surface. Well, that's a quite complicated problem, and I didn't touch it because it would require really a lot of explanation. So you are right, because of course, if we measure from the scalp, this information is very much blurred because the electric signals are damped by the skull, by the skin, also by some fluids which are between brain, and so they are damped. And as I mentioned, like especially high frequency are damped. So there are a lot of work connected with solving so-called inverse problem, that is to finding the sources in brain based on the measurement on the scalp. And it's really hard problem because as we know from physics, is non-unique problem. Inverse problem is non-unique problem. And then the very crucial thing is where we assume primary source, because we have to assume and then teach. However, in the case of, because we have a component which is called volume conduction. So not the conduction through the nerves, what we would like to know, so the axons, but the propagation of electric field, which is in the brain and outside. In fact, we measure it. But DTF has one advantage because it is based on phase difference between signals. And volume conduction is propagation of electromagnetic field, which propagates with zero delay. So in a way, DTF is not, we can say that it's totally independent, that it's not affected by volume conduction. But volume conduction is to the certain point mitigated. Of course, there are so-called, there could be the influence of the secondary sources, and there is now a very big discussion how much the TF is or is not blurred by this volume conduction. But let's say this experiment about gamma, in fact, this gamma activity is really very hard to see because of this damping, and it's quite well recorded, and not recorded, but it's found by DTF. Why? Because this volume conduction is to a large degree mitigated by the fact that it takes into account only phase difference. But it's really a very serious problem. There a lot of work on it.
Other questions? Maybe from the people connected via Zoom. So please raise the hand. Oh yes, Staszku. Okay, I think you can. I think, can you speak? Yes, please do. Staszek.
It is very bad.
Very distorted voice. Can you repeat your question again?
Can you repeat, or maybe you can write or something,
Right
because
on chat.
it's very much disturbed. I cannot
Maybe
get
you can
it.
write it in the chat.
Maybe in the chat, because I don't understand.
Can you hear me now?
Yes, now, yes, yes, okay.
Okay, I have a little bit odd question because I understand your talk was mainly about movement of fingers and simplified events that could be analyzed using the signals you measured. But I'm very curious about the current status of prospects for understanding how the brain stores language and how the meaning of words is located in the brain and how we use the words in context in which we talk. And is there any chance of understanding more about it?
Yes, yes. In fact, it's a pity because now they open it is really very difficult when we measure the signals just from the scalp. But in this Johns Hopkins, they remove part of the head before the surgery. And it's quite a common thing that the epilepsy foci are in temporal lobe. And the sounds and the meaning of words are this so-called verbal cortex is in the temporal lobe. And they, in fact, they determined the propagation during, in such experiment that they were words spoken and repeated. And they determined this by means of DTF, and a very interesting result. I even had this movie, but then I thought that maybe it will be too much. So maybe you should look at the works of, if you are interested, of Anna Korzeniewska, Nathan Krohn, Piotr Pranaszczuk. Maybe you can see in the internet their work, quite recent, exactly about this problem.
Thank you very much.
Other questions from the internet? I don't see. I think it must be really fascinating to be able to understand how the brain works.
Yes, but it's, you know, of course, it's the best if we can measure it on the surface of the head, but it's a small chance to do it. Of course, there are some animal experiments, but
Yeah.
it's not the same.
Okay, so if there are no more questions, so let's thank the speaker again. Thank you very much. The last colloquium this academic year, so see you next year.
Patrzę, gdzie tu się wyciąga.